Hey everybody! All right, so today I am I'm running the video. So I thought for this asynchronous video we could just take formal notes with some slides, and I'd like to thank Mr. Rowley for making these slides. He made some great ones, so I just decided to use them. All right, so let's move on here. So I'm going to show you this in class, and we'll talk about it. But I can float a needle on water, and the reason is water has high surface tension because of the intermolecular forces in water. So, by the way, on your notes, you want to write down intermolecular forces. We're going to talk all about them now. If I go too fast, pause the video. If I go too slow, sorry. All right. What are intermolecular forces? IMFs. They're forces holding different molecules together. They are located between molecules, right? So they're not inside molecules. They're not the forces we've been talking about all along so far. We've talked about bonds that hold atoms together, right, which make molecules. No, these are forces that hold different molecules together. That's what intermolecular forces are. There's three different types of intermolecular forces. You've got your London dispersion forces, dipole-dipole forces, hydrogen bonding. What determines if a substance is a liquid, solid, or a gas? Let's talk about it. Liquids and solids and gases are, if an object is a liquid, a solid, or a gas, that is determined by, that's determined by the intermolecular forces and the temperature that the substance is at. So gases are totally disordered, right? The intermolecular forces that may exist between the gases are completely overwhelmed by the amount of energy they have inside them, by the temperature they're at. So they're just flying around and they act like there's no intermolecular forces whatsoever. Totally free to move around however they want. That's what gases are. Liquids are stuck together, but they're sort of like they can still move around each other. So it's disorder, but it's like clusters of disorder. And they move relative to each other, but they are close together. And gases are totally stuck together. Usually, they're closer together than liquids, although water is a exception to this rule. They have a very ordered arrangement. They're pretty much in fixed positions. That's how the molecules act in a solid, liquid, and a gas. And of course, the colder, if something's very cold, it'll be a solid. If it's at a medium temperature, it'll be a liquid, and if it's very hot, it will be a gas. Just think about water: ice, liquid water, steam, right? Okay. London dispersion forces. These are pretty weak. These are the weak ones, all right? So they result when electrons in a nonpolar molecule become unevenly distributed. So think of a nonpolar molecule as being like kind of squishy, and it can have a little bit of a slight dipole to it, like a little bit of an offset of charge, and that causes intermolecular forces. And this tends to happen. This happens in This happens in your nonpolar substances. So if something's nonpolar, you know that it's going to have London dispersion forces involved. Dipole-dipole forces are the other type of intermolecular forces we're going to talk about. They occur between polar molecules. So the dipoles align so that the positive end attracts to the negative end of a neighboring molecule. All right. I showed you this in class when I talked about water. Although when I talked about water, I was talking about hydrogen bonding, which is a very specific type of dipole-dipole that we give a different name to. Dipole-dipole forces are typically stronger than London dispersion forces. Okay, that's kind of what the dipole forces look like. You see this blob here? It's got a partially positive end and partially negative end. Well, the partially positives are attracted to the partially negatives, but the partially positives are repelled by the other partial positives. So there's got repulsion forces and attraction forces, and it makes it arrange in kind of a symmetrical, an orderly fashion for the most part. Hydrogen bonding, that's our third type. This is technically a type of dipole-dipole bond, but it's a specific one that happens between hydrogens and oxygens, hydrogen fluorines, or hydrogens and nitrogens. So if something's got hydrogen and oxygen in it, and it's polar, then you know it's going to have hydrogen bonding. If something's got hydrogen and fluorine in it and it's polar, it's going to have hydrogen bonding. It's got hydrogen and nitrogen in it. It's polar. It's going to have hydrogen bonding. All right. So hydrogen bonding is typically stronger than other IMS. It's the strongest type of intermolecular force. Okay. It's stronger than, they should say London dispersion forces and dipole forces. But that's okay. It's stronger than the other types. So let's try to practice. Let's try to figure out what each of these types is. So I want you to pause the video now and try to figure out what type of intermolecular forces these have. Are they London dispersion forces? Are they dipole, or are they hydrogen bonding? You're going to pause the video and check it out and try that on your own. All right, welcome back. So let's talk about it. HCl. Okay, that's a polar molecule, and it does have hydrogen, but it doesn't have nitrogen, oxygen, or fluorine. And so it's not hydrogen bonding. It is just normal dipole bonding. Let's look at number 2. Hydrogen and fluorine. Well, it has hydrogen in it. It is polar. It is a polar molecule. And it's got hydrogen in it. And it is fluorine. So that must have hydrogen bonding. All right, let's look at carbon dioxide. Number 3. Carbon dioxide, remember, it's got those double bonds. And so there's no... so all of carbon's electrons are involved in bonding, so there's no lone pairs, and it's a linear shape, so it is nonpolar. And nonpolar molecules are going to have London dispersion forces involved in them. So those are the intermolecular forces there. Let's look at number 4. NH3. Well, NH3 is going to be, let's see, 1, 2, 3, 4, 5. It's going to have a lone pair on the nitrogen. And so it's going to be like a trigonal pyramidal shape. If you learned that already, it doesn't matter. It's going to be a polar bond. And now that I said it's polar, if you didn't know it was polar before because I didn't draw the Lewis structure, figure out, is that going to be polar? Is that what kind of intermolecular forces is that going to have? NH3. Okay, we're done. So it's got hydrogen and nitrogen. So that's going to have hydrogen bonding. Okay. All right. Carbon monoxide. That is just 2 atoms, and they are kind of far away from each other on the periodic table, so they have a different electronegativity. They are polar. So that's a polar thing, but it is not oxygen and nitrogen, or oxygen and fluorine, or oxygen and hydrogen. I'm sorry. It's not hydrogen and oxygen, hydrogen and fluorine, or hydrogen and nitrogen. It's hydrogen. It's carbon and oxygen. So it's definitely not hydrogen bonding. Of course it's not hydrogen bonding. I don't know why I went there. There's no hydrogen involved. So that must have dipole bonds. Number 6, you got your carbon and your hydrogen, C2H6. That is going to be nonpolar. You do have hydrogen, but you don't have nitrogen, fluorine, or oxygen. And so this is going to have... This is nonpolar. Did I say polar? I hope I didn't. This is a nonpolar, so it's got to have London dispersion forces. If it's nonpolar, it's London dispersion. If it's polar, you look for hydrogen and nitrogen, hydrogen and fluorine, or hydrogen and oxygen. And if it has those, then it's hydrogen bonding. If it doesn't have those, then it is dipole. All right, moving on. I'm trying to move on. All right, let's look at these boiling points. We want to predict a trend here. I don't care about predicting a trend. I want to look at something interesting. Look at hydrogen. Look at H2O. And then look at H2S. Now notice that sulfur is right below oxygen on the periodic table. And notice that selenium is right below sulfur. And notice that tellurium is right below selenium. So water is way up here in terms of its boiling point. I actually think this boiling point should be at 100. Something went wrong with this 100 should be up here. So just sorry. But water boils at 100 degrees Celsius. So I'm not sure why that's not up there. There was a mistake. I transferred this over to a Google Doc and it got messed up. But what are you going to do? Anyway, either way. So water's way up high. Its boiling point is really high up, right? But then if you have two hydrogens and a selenium and a sulfur, it's like all the way down here. It's like got a much lower boiling point. It's like lower than zero or something. I'm not 100% sure. So what does that what must that mean? Well, water's got different bonding, right? That's hydrogen and oxygen. That is hydrogen bonding. So hydrogen bonding must have higher boiling points. And then that's not hydrogen bonding, but this one is this water and hydrogen and selenium is really similar to hydrogen and sulfur, although it's a little higher boiling point. And then hydrogen and tellurium is a little bit higher boiling point as well. And these atoms are a little bit bigger. Tellurium and then selenium, they're a little bit bigger than sulfur, so maybe that's what's going on there. Over here, when you have carbon and then it seems like with these, the trend just goes up and up and up as the molecules get bigger, as the atoms get bigger. So you've got carbon, and then you'll look, and silicon is right below carbon, right? And germanium is right below silicon, right? And tin is right below germanium. So the only difference between these molecules is the size of the atoms. And as the atoms get bigger, the boiling point goes up. So that's interesting. So this asks us to predict this trend. We're just going to look at it. Look at this. Hydrogen bonding, higher boiling point, right? And then you got nitrogen. Phosphorus is right below nitrogen on the periodic table, so it's going to have very similar properties, right? And then you've got arsenic, which is right below phosphorus, right? So, and then you've got antimony, which is right below the arsenic. And so the nitrogen bonding has a high boiling point. That makes sense. And then the very similar molecule, but no nitrogen bonding, has a much lower boiling point. Similar molecule with a bigger element involved, higher boiling point. Similar molecule with a bigger element involved, even higher boiling point. So I think we're starting to see a little bit of a trend here. Let's see. Here's just a bunch of different things all mixed together here. And these are, you notice that there is trends with the groups on the periodic table. As the elements get bigger that are involved, you end up getting higher boiling points, unless they have hydrogen bonding, in which case the hydrogen bonding has the highest boiling point. So let's put that all into writing. It's going to be a decent amount of writing. Intermolecular forces in boiling point relationship. Stronger intermolecular forces cause an increased boiling point. Weaker intermolecular forces cause a decrease in boiling point. Why? Because IMFs require heat to break down. So the stronger the IMF, the more heat is required to boil the liquid, which results in a higher boiling point. IMFs that's the strength of the bond. If you've got a really strong bond, you need more heat to break that bond. Liquids with lower IMFs require less heat, which results in a lower boiling point. Okay. If molecules have the same IMF, the one with more electrons will have a slightly stronger intermolecular force and higher boiling points. The reason that is because they're easier to polarize because they have more electrons. Okay, so the ease at which an atom or molecule can be distorted to have a momentary dipole. Okay, what does it mean? Larger molecules are more easily polarized than smaller ones. This means molecules and atoms have the same type of IMF. The bigger one will have a stronger IMF and a higher boiling point. Okay, to be honest, guys, this always kind of got a little beyond my mental capacity, polarizability. But I was able to know that the larger the molecule, if it's got the same type of intermolecular force, if it's a bigger molecule, that's the one that will be a stronger intermolecular force, and that's the one will therefore have a higher boiling point. I don't want to do this question. That's it for today, guys. Thanks for watching. I'm sorry I went a little over 10 minutes. Have a good one.